Sweet. Hi, everyone. So my name's Ollie. I'm supervised by Yansing, Ko, Jorg, and Moritz. Yansing and Moritz are here today. And I'll be talking to you today about my work in my PhD, which is on machine learning for water quality monitoring. So firstly, a quick outline of the talk. So I'll be briefly talking about the problem description, the motivation that motivates my work. So apologies in advance to people who have already have already heard this a few times over my time in this PhD. I'll then be talking about some of the challenges and solutions I've tackled in my PhD, and finally a bit of a few comments on bridging the gaps between the disciplines that I've come across in my studies. So firstly, what is water quality monitoring? So it turns out that it's quite important to monitor the quality of water, particularly in lakes. And one of the key reasons for this is you get harmful algal blooms. This is where you get a rapid buildup of algae within a lake or water body. And this can be harmful to local ecosystems, aquaculture, and even human health. These being cases of deaths for this. I don't think in New Zealand, but it's a serious issue. And so lots of lakes all around the world are monitored for their health. And so the task I'm working on is trying to see if we can use remote sensing, which is in this case when we're using satellite data to try to predict the concentration of certain interesting constituents in the water, such as chlorophyll, which is sort of an indicator of the health of the water. And so more specifically, the task is to, given the color of the lake, so we're looking at a per pixel basis, we're not looking at images because of the spatial resolution. We're looking at the color of the lake, and more than just red, green, and blue, the satellites measure light in lots of different frequencies. And we're trying to predict the concentrations of these constituents of interest. So this is a regression problem with tabular features. And so the first thing that makes this problem a bit hard and interesting is that ground truth data collation is expensive. So these data sets end up being quite small. So to prove my point, I've got a picture of Moritz up here on the screen. And so he's out here on a lake doing difficult environmental science work. And all of that, going out on a lake, getting a sample of water, taking it back to the lab, analyzing it, that's for one data point. So as you can imagine, the data sets are not that big, a couple hundred data points typically for a national data set. However, in contrast that, the unlabeled satellite data, so just the raw satellite image, it doesn't have any ground truth value associated with it, is abundant, effectively unlimited, right? You can get as many pictures of satellites, of lakes, as you could possibly want. And so the first question I tackled in my PhD was whether we could use unlabeled data to improve the modeling. So for you that are familiar with machine learning paradigms, the idea of semi-supervised learning might come to mind. So this is the idea of using unlabeled data to improve model performance, which at first seems like a bit of a contradiction because we're using data that doesn't have any ground truth value to learn more about the relationship between, the satellite image and the ground truth concentration of the constituents. However, if we make certain assumptions, we can actually use this data to help us. And the way I like to think about this is that if we have a large sample of different colors of lakes, we can actually learn what kind of lake colors exist and what the distribution is of the different, colors that lakes can take. Much more than if we were just using the small data set we have access to. And so if we make certain assumptions across that distribution of different input data, the lake colors, such as that the data set is smooth. And so, for example, two lakes that have similar colors, you can expect them to have similar concentrations of constituents. We can actually improve the performance of our models. So that's semi-supervised learning. The issue was that one of the popular algorithms for water quality remote sensing are mixture density networks. And that existing semi-supervised learning methods cannot be directly applied to mixture density networks. And so I won't go into any details, but we proposed a method called Wasserstein-Laplacian regularization to apply semi-supervised learning to mixture density networks. And so here's a few diagrams of how that works. But the cool result that we found from this is that we're able to, by using this unlabeled data, improve the performance of our algorithms substantially. So what we found was that for a typical regional data set that might have a couple hundred data points, we're able to get, by using the unlabeled data, an performance that was equivalent to if we have a data set that was 50% bigger. So if you can think of how much effort it would be to collect those data sets for years to get that extra size, that's quite an exciting result. Next challenge we looked at was looking at lake differences. And what I mean by this is that in the recent years, we've started getting a trend of global collaboration within the water quality remote sensing community that has led to some large data sets being collated. And so this is this screenshot here that sort of summarizes a recent data set called Gloria, once again named by Moritz, which has lakes from all around the world of all different types of, lakes, wide variety of lakes here. And so machine learning methods have started becoming more popular for this reason as well. The issue is that different lakes are known to have different mechanisms. So, for example, here on the left, I've got Lake Waikare, which Vanessa just briefly mentioned, which unfortunately has become the poster child for a lake that's a bit dirty in my talks because it's very shallow. There's lots of fish jumping around and making, swirling things up. And in contrast to that, you've got Lake Taupo, which is very deep, and the algae in there just behaves entirely differently. And so you can think that lake-specific models should be able to perform better than these global models that have been performed, right, to model these lake-specific characteristics. However, the issue is that there's not enough data per lake. Although we've started creating these large global data sets, the amount of data set you have data per lake is still generally not large enough to make a lake-specific model, sorry. And so once again, those of you who've spent some time in machine learning might be thinking of multitask learning. So this is where in machine learning, we want to learn multiple similar tasks, is what we call them, which in this case, each task is trying to predict the water quality of a lake given the color of the lake. And you're trying to learn multiple of these tasks simultaneously, and that improves performance by sort of sharing knowledge between the lakes. So if you're learning a model for one lake and a model for another lake, there's actually a lot of knowledge in each of those models that's actually transferable between them. And so by sharing that knowledge using transfer learning in a multitask learning setting, we can actually improve the performance across all lakes and make task-specific models, even though we don't have enough data per lake to train these models individually. And what we thought as well was we can take this one step further. So we can use metadata. What do I mean by metadata? Well, in this problem, we've actually got quite a cool opportunity that we have data about the lakes themselves. So this can be thought of as task level information. And this is things such as the depth of the lake, the temperature of the lake, the climate, the biome around the lake. And these things are actually really informative with regards to which lakes are similar to each other. If you can imagine that two lakes are both deep, cold, and I don't know enough lake science, but if two lakes have very similar characteristics, you can imagine that the mechanisms of algae and of water within those lakes will be similar. And so what you would want to do with that is that in the machine learning model, you would want those two lakes to have a lot of knowledge transfer between them, which actually answers one of the difficult questions in multitask learning, which is which tasks should you be transferring knowledge between, right? You've got all these tasks, and maybe some of them are more similar than others. Maybe these lake level information could help answer that question. Once again, existing methods cannot use metadata effectively because it's sort of task level information that doesn't really fit in with the data set naturally. So what we did was we proposed multitask hypernetworks. This is a multitask learning architecture that can leverage task level metadata. And so just to briefly summarize the architecture here, we've got a hypernetwork, which is shared among all tasks. And a hypernetwork is a neural network that outputs the weights of other neural networks. So it gets a bit confusing, but effectively we have one neural network per task, and these weights are all generated by the same hypernetwork, but the hypernetwork takes as input metadata that's specific to each task. And so we're learning for each task, for each lake, we're learning a relationship that's conditioned on the metadata for that lake. And so we're able to learn these lake differences from the metadata for that lake, which is quite cool. And again, here we find that we have good performance compared to other multitask learning methods, especially when we have available metadata. So that's the two things so to summarize the two things I've briefly talked about, we've proposed two novel and exciting machine learning methods, and they're specifically designed to handle this problem of environmental data and some of the interesting data characteristics that come up in this problem. And the hope is that over time, these methods may become widely applied by the community. However, it must be said as well that sometimes machine learning work can take time to actually reach the practitioners. We're publishing in different conferences. It just takes time for the knowledge to spread. And I think that's one of the cool things about this TAIAO platform is that we're sort of helping bridging that gap of getting the knowledge from abstract machine learning journals and into actual use. And so one of the other things I'm trying to do with that is to apply maybe more traditional machine learning models to this problem. And so we've started work that we want to submit to an environmental science journal, where we're trying to use more traditional machine learning methods. In this case, the original multitask learning architecture that's shown on the right there, and it's from 1997. So from machine learning view, this is not the most revolutionary idea. However, it turns out that this is an idea that's quite useful for modeling this problem and hasn't really penetrated the ecosystem of environmental academia yet. And so some quick experiments show that this idea of multitask learning can have very drastic improvements in performance when looking at these global data sets compared to looking at things as a single task, which is what was done before. So just to finish off, I guess a quick comment on how I'm sort of thinking about this, which is that the intersection of domain knowledge and machine learning understanding is quite valuable. So I've got two bubbles there in the Venn diagram. On the left, people with a knowledge of machine learning systems. On the right, people with knowledge of water quality monitoring. There's a lot of people in each bubble. There's few people in the middle. And from my personal experience, I've learned very little. I have very shallow understanding of the knowledge of water quality monitoring, but that's still actually enough to sort of come up with some ideas that connect the two, bridge the gap, and can be very useful. And so, yeah, implementing these machine learning frameworks to new fields can be a really exciting and cool contribution. So yeah, that's all for me. Thanks for listening.
Thank you, Olivier. We got
we
got 10 minutes for two burning questions. Yep, please.
In terms of the ground truth data collection, is it collected working with models of local councils that program? What do you recommend with local councils? What is happening?
Yep, so I can't claim the hard work on that, but lots of environmental scientists are going out collecting the data. Often researchers are going through the effort of collating the data from different regional councils, putting into single data sets and quality assurance. And then the third step from that is that in recent years, people have started doing that from data sets from all around the world and collecting all these data sets from different countries, from different regional councils and getting it together. But often at the origin, they do come from monitoring programs such as regional councils. Yeah.
Thank you.